I want to discuss a little bit about electric fields. So, just a recap of everything we've done so far. Actually, not a recap. I'll use this as a tool to introduce electric fields. So, if I have a charge, let's say Q here, and I have a charge, let's say capital Q here. So, you and I know that there is a force acting on this, and then let's say just excuse me for a moment here. I'll erase this. Let's say I have somehow kept it in a container or something. I mean that it cannot move. Okay, so then in that case, let's say that this one is Q, small q, and this one is capital Q. Then in this case, this charge is not going to move, right? But this charge is going to experience a force, though small q is also experiencing a force, but the container somehow opposes that force and doesn't let it move. Okay, so this one will experience a force F. So we just discussed that F, the magnitude of F will be K, Q, Q. Both are of different cases. One is uppercase, one is lowercase. And if I say that this distance here, this distance is, let's say R, or yeah, R, then this is KQQ by R square. Now, what I want to I want to introduce a concept or property which is like a fundamental property of this charge only. I mean, it doesn't matter whether you bring capital Q or yeah, I don't know, Z or any other charge. I mean, it can be negative Q as well. It doesn't matter. I want to derive something which is a fundamental property only of Q. I mean, whatever that property is, it should be independent of capital Q, right? So, what if I divide in this equation? I divide both sides by capital Q. So then, what will I get? I will get F divided by capital Q will be equal to KQ, where Q is the small one, by R squared. And now you can see that this term here, it is just a function of the charge itself and as well as the distance at which you are from the charge. So it is independent whether you bring minus Q or plus Q or any other charge. It doesn't matter. This quantity is a fundamental property only of small q. So this quantity here is defined to be the electric field, which is a vector, and by the way, force is also a vector, but I won't show it now. Electric field at that point R, at that point which is at a distance R from the small q. Now, electric field is defined to be a force per unit charge. Now, how do we visualize this? Now, imagine that we have a charge here, which is of the same, let's say, small q, and we are at a distance. We are at a distance small r from the charge q, and this is a circle, even though it doesn't look like. Then we say that the electric field at in that circle, or you can say sphere, looks like this somewhat. I'll draw a rough diagram here, not a precise one. It looks something like this, and these all arrows are of the same magnitude because Q is constant, right? But when we are in a circle, R is also constant. actually that is the definition of a circle. The radius is constant, right? So the whole term must be constant, which implies the electric field must be constant. Well, not vectorially, but magnitude wise. So there you go. It looks something like that. So you can imagine that farther away R is going to increase, but Q is going to remain the same, right? This will remain the same. So if this increases, then this has to decrease, right? I mean that if this is 4r squared and then increases to 5r squared, then this will definitely decrease, right? So it also kind of makes sense, because the farther away you are from the charge, the less force you experience, right? So we define force now in we think of force in terms of electric field now. It is a better thing to imagine, visualize. So we say that the force, if I multiply F by Q is E, right? So if I multiply both sides by Q, then I get F equals Q times E, which implies that if there is an electric field which looks something like that, and let's say it has a magnitude E, then if I bring a charge of magnitude capital Q, and this capital Q is the same as this capital Q, if I bring a charge of capital Q in that electric field, it will experience a force equal to the product of the charge and the electric field, and that force will be the same in the same direction as E, which implies that the force will be in this direction. So the charge is going to move away. Now if you bring a negative charge in place of positive one, you can imagine that the magnitude will be the same, but this will become a negative, so the force will be in the opposite direction as E, which implies that it moves like that. So it is actually the truth that if you have an electric field and you put an electron in that electric field, then it will move opposite to the electric field. I mean, it will move like that. But if you put a proton or a positive charge, it will move like that. So now from now on we'll think about force in terms of electric field. Okay, so it's kind of very nice to express some terms. Okay, so that's all about electric fields. Now this was a concept introduced just to simplify things a bit. It is nothing more than a rearrangement of Coulomb's law. So in my next video I'll talk about a little bit about electric potential energy, and you have to be very careful because there are two terms there: electric potential energy and electric potential. Both are two very different concepts, actually not so different, as you'll see in a few videos. Okay, so I hope you like it, and from now on we'll just, I mean, if I say that there's an electric field, there's a Q, you immediately it should come to your mind that it'll experience a force in this direction, and it has a magnitude of Q times E. Okay, so I hope you like it, and I'll see you in the next video, in which I'll introduce to you the concept of electric potential energy.